Okay, so now we will have to prove a similar lemma for the external potential case. A similar lemma than the first theorem in H1 without the external potential. So the lemma will be, um, well, let's suppose mu greater or equal than 0, okay, and let B satisfy assumption 1. Okay, recall assumption 1. Assumption 1, we had that B is B plus B minus, and B plus is in L1 log, and B minus is minus Laplacian 1/2 form bounded. Okay, so B satisfies assumption 1, and so the map Ju E minus mu x convolution U squared U is locally Lipschitz, continuous from X, recall X, energy space into itself with Ju minus Jb norm X is less than equal within a constant then U x squared plus B squared x U minus Bx. Okay, this is for all UB in X. Okay, so a similar lemma than the one we have in the first, it will be the lemma 4. So the proof of lemma 4, but we can do the same that we did in lemma 1. Recall that we have this norm equivalence, so we will have to bound this part. Okay, so by lemma 1 we have that Ju minus Jb norm H1/2 is less than equal within a constant to U squared H1/2 plus B squared H1/2 U minus B H1/2. Okay, so now we will have that this is less than equal, then U squared in X plus B squared in X multiplied by U minus B X. Recall that the norm of X is the square root of U B, this inner product, and QUU, which is we have the operator in a scalinear form, and then we have the B minus and the B plus. So it is a bigger norm, so we can bound by this. Okay, so we estimate this, and now we have to estimate B1/2 U. Okay, B1/2 plus is that here it is the plus. So what happens with the other? So we have B1/2 plus Ju minus Jb, norm 2 less than equal than, okay, is less than equal than the bound that we've been using in all the theorems. b1 half plus of e minus mu x convolution on u squared minus b squared close and u plus b. Norm 2 plus, and then we have the other term that it would be similar, but now we will have instead of a minus here we will have a plus, and in the other part we will have u minus b. Okay, norm 2. So once again we can bound this using hello, this is less than equal than e minus mu x convolution u squared minus b squared norm infinity b1 half plus u plus b norm 2. Okay, so recall that this is a L1 log function, so it just came with this part. So then in the other term we do the same thing and we will obtain e minus mu x convolution u squared plus b squared norm infinity b1 half plus, and in this case it will be u minus b norm 2. Okay, so now we will use what we knew about how to bound this term in dilemma 1, that we have similar both terms. So we can bound first this one by u plus b h1 half u minus b h1 half b plus 1 half u plus b. Okay, so this stays the same, and these two come from the way we bound this. And the second term will be, well, how we bound this in the first lemma, and that will be u norm square norm h1 half plus b square norm h1 half. Well, and then what we have left is b1 half plus u minus b norm 2. Okay. Okay, so now what is left is to notice again the equivalence between the norms. That will be very important because we will have that u h1 half plus b 1 half plus u is less than equal than u h1 half. Sorry, x. This is norm x, and again we will have u h1 half plus b 1 half. This is norm 2. So notice that, for example, this u plus b in h1 half can be bounded by u plus b in x, and both of them can be bounded by u in x and b in x. The same can be done with this, and we will have again u in x and b in x. Like that, we will obtain u squared x plus b squared x. The remaining, this can be also be bounded by x. And the same we can do with this term, because we have u squared h1 and we will bound it by this also by this, and this will be bounded by u minus bx. So we will obtain within a constant this bound. So this proves the lemma. This was the big work that has to be done, because then we just simply know that we have to now E minus ETA is like we call C0 group of isometries. So like we did with the other theorems, well, in this case we just had to clarify that A is minus Laplacian plus m squared plus b. Okay, so the nonlinearity is locally Lipschitz on x, and so you have local Bosons, the same way as theorem. For global world Bosons, we will have to prove a conservation of charge and of energy. Okay, it will be the same thing. There is not much work to be done or new work, because it will be the same thing. Just to clarify what it is, the energy is when I have you conjugate x, the operator ux dx plus we have this extra term which contains the potential multiplied by ux squared dx plus 1/4 all 3 lambda, well, the potential, this is a minus mu x convolution u squared, and of x and ux again squared dx. This will be the energy. So once again we have to employ our regularization method. We again have to use the m epsilon, recall EA plus 1 to the minus 1, the regularization method. Once again m epsilon, but now with this a, where if you recall it will have the 3 properties. Okay, so it will take from x to, well, we can say x plus 1, okay, just leveling the space, which that leveling can be done by the spaces xs. The norm xs will be 1 plus a s over 2 u norm 2, okay, and in the same way m epsilon acts on the embedded spaces x plus 2 embedded in x plus 1, x minus 1, okay. So with this you can prove the 3 properties, and the rest of the argument for proving conservation of energy, it's the same as in the theorem of global world postulates for H1 with without major modifications. So for the a priori bounds, it's the same way. Just know you have to take care that B minus is a minus the Laplacian bound form, okay, and so one has to take care to bound that correctly, but this are just the same ways that we just been doing with the other theorems. That will complete the proof, but the approach is the same for all. Okay.